Swayam Prabha. Digital India. Educated India.
In this lecture, we are going to again carry over the thermodynamics of solution. As I have discussed in the last class that solutions are actually atomically mixed solid solutions. That is what we have treated. So, now we are going to use this mathematical formalism for answering different aspects of solution. So, solutions can be formed in many ways, but thermodynamically we can think of a solution forming in two steps. In the first step, if a solution contains two atomic pieces A and B, then we bring them together side by side. This is step 1. In the steps 2, we allow them to mix mechanically. Now, in the step 1, if the solution contains x moles of B and 1 minus x moles of A, then the mixture will have free energy given by Ga0 1 minus x plus Gb0 x, because we are taking x mole fractions of B. So, therefore, the free energy of the contribution of the B will be x multiplied by Gb0, where Gb0 is the free energy of pure B. Similarly, free energy of pure A is Ga0, and there are 1 minus x mole fractions of A in the solution. So, therefore, it is Ga0 multiplied by 1 minus x, and if you take the sum, then it becomes Ga0 1 minus x plus Gb0 x. And as I told you in the last lecture, that this is the equation of a straight line. If I plot G of free energy versus x, x is the mole fractions of B. So, at any point on this curve within pure A and pure B, the free energy is given by a point lying on this line. So, that is basically nothing but free energy of the physical mixture or mechanical mixture, that is we have put things together. Now, what happens when we atomically mix them? Okay. So, let us do that on a board, that is much easier. So, if I consider the, so I have already told you the free energy of the mechanical mixture is nothing but 1 minus x multiplied by Ga0 plus x multiplied by Gb0, okay, where this 0 stands for the pure elements free energy. Now, this is my step 1. In step 1, I have just mixed the two elements in the proportion of 1 minus x and x, and the steps 2, the mixing will be done atomically. Now, how do I calculate that? Okay. So, this to calculate that, let us assume that G1 is the free energy of the after the steps 2. So, obviously, G1 will be G plus some additional term, which is delta G. Delta G is because of the mixing, atomically mixing of these two pieces. This is just a mechanical mixture. We can write down also mechanical mixture. Now, if you add them together atomically, if just like a solution, let us say if you add sugar in water or if you add coffee in milk, then what will happen? The free energy of total system will be equal to this G plus an additional term, which will come because of the mixing, atomically mixing together. So, this is because of atomically mixing, because in a syrup, in a sugar syrup or in a coffee and milk mixture, atoms are mixed atomically. So, what is happening if I mix atomically? We know that G is given by free energy. I assume you know all this stuff, because I have already told G is given by H minus Ts, where G is the Gibbs free energy, H is the enthalpy of the mixture, enthalpy of any system, T is the temperature and S is the entropy. So, therefore, delta G is nothing but delta H minus T delta S as at a certain temperature T equal to T, right. That is what we know. So therefore, I can simply write down G1 is nothing but G plus delta G, that is equal to G plus delta H minus T delta S. This is my first equation, which comes if I atomically mix two PCs in a proportions of 1 minus x and x. Now this G is directly coming from the mechanical mixture. What we need to calculate is delta H and delta S. So that is why actually we are going to make assumptions to calculate this. The first assumption we make is that of an ideal solution. Okay, what is ideal solution? Ideal solution is one where heat of mixing is 0. That is, if I put A and B together, there is no change of heat. Okay, if A has certain enthalpy H A and B has certain enthalpy H B, and if I mix them together, the enthalpy of the system is become H A plus H B minus H A B, that is equal to 0. So that is what is delta H. So therefore, delta H is assumed to be 0 for ideal solution, and ideal solution is one where there is no heat of mixing or volume change because of mixing. That is what is the assumption for the ideal solutions. And if that is the case, if delta H is 0 for the ideal solution, then G1 become G minus T delta S. Okay, that is at a particular temperature, where T is the temperature and delta is the change of entropy. So obviously, to calculate this we need to know what is the change of entropy. The reason I am just going step by step is because calculation of enthalpy requires many important aspects to be understood, but calculation of entropy is much easier. Now as you know, entropy has two important parts. What are these parts? One is a thermal entropy, or what is known as vibrational part of entropy, other one is known as configurational entropy. So what is vibrational entropy? If I heat a system, the atom starts vibrating, so therefore energy levels of atoms will have different characteristics, and that is contributed to entropy because of the thermal aspects. Normally in metallurgical thermodynamics we ignore this part because this is not a substantial amount in case of solutions. And second important part, so therefore entropy is equal to this plus this, as I wrote, total entropy, and as I told you, the thermal part is ignored because of its contribution is not very high, that is why. And what is the second part? This is known as configuration part. Now if I take two atoms A and B different types and started arranging them in a lattice, that is why you form the solutions. There is change of configuration as compared to pure A and pure B. If I have only pure A atoms and try to arrange them in a lattice, then there is only one possible of arrangements. Similarly, if I have a pure B, try to arrange them in a lattice, there will be only one possible arrangement of pure B in the lattice, because the atoms are similar or same. But the moment I have two atoms, different chemically different species, and try to arrange them in a lattice, I can have many ways of arranging them. That depends on what are the different probabilities of arranging them in the atoms in the lattice. So that is what actually contributes to the configurational entropy. Configuration means different types of arrangements, and these different types of arrangements will have different probabilities. Obviously, the one which has the best or highest probability of all the arrangements, it will be observed in the real systems. So this is the part which is now normally contributes to the entropy, and that is the part we need to calculate. So therefore delta S, which is shown here in this term, is directly coming from change of configuration entropy. This part is ignored. It has been observed that this part, the thermal part, contributes only 1.5 to 2% of the total entropy change. That is why this is not considered in the general sense, but specifically we should write down this is almost equal to configuration entropy change. So then how I calculate that? Okay, that is what I am not going to do in details, but I am going to tell you how it is done. It is done from Boltzmann's equation again. Boltzmann's equation is what I showed you in the last lecture. This is S equal to K ln W. So, K is nothing but a Boltzmann constant and W is the different possible elements of the atoms in the lattice. Okay, that is the probability actually, and log is log of that probability what determines the entropy. So, it is a standard derivation which is there available in the books, and one can do also. It is not very difficult task. Using Stirling approximations one can calculate that, and for a binary alloy it is equal to K multiplied by N, K multiplied by capital N into x A log of A, that because of that log comes here, x B log of x B. For our system we can write down minus K N multiplied by 1 minus x log of 1 minus x, because x A mole fraction is 1 minus x, that is why, and x log of x, that is from B. So, that is what actually we get if we do the detailed calculations. So, I am just skipping it because it is there in my phase diagram course, also is available in the books. So, then I can write down that is nothing but G plus KTN multiplied by that factor 1 minus x log of 1 minus x plus x log of x, okay. And that is become G plus K and N. If you multiply Boltzmann constant with the atomic Avogadro number, that becomes the gas constant. Gas constant is what? R, capital R, that is the universal gas constant, that value is 8.314 joule per Kelvin mole. RT 1 minus x log of 1 minus x plus x log of x. So, that is what is the equation we should use. So, I will just erase the steps 2 part to write down the equation properly, so that it is visible. So, at the end of steps 2 what do I get? I get G is equal to G1 actually, G plus R into T 1 minus x log of 1 minus x plus x log of x. So, that is nothing but, if I write completely this term, that is nothing but 1 minus x GA0 plus, I am just plugging this value of G from the top equation, x GB0 plus R into T 1 minus x log of 1 minus x plus x log of x. So, that is the free energy of ideal solution. That is why I write here G1 ideal, okay. That is the free energy of the ideal solutions. If I mix 1 minus x mole fractions of A and x mole fractions of B. Now, if you clearly see this is an equation of a straight line, right. This is an equation of a straight line. What about the next part? Let us see what happens to the next part. We know that if x is a fraction, when x is a fraction, very small fraction, suppose if that is the case here, then log of x is nothing but x, or 1 minus x rather, not x, okay. That is what happens. So, if I simply use that from that analogy, so then I could see here that equation G1 ideal can be written as straight line functions 1 minus x GA0 plus x GB0 plus RT, okay. So, if I write down this, so therefore 1 log of 1 minus x is nothing but x again, okay. So, that has become 1 minus x multiplied by x. So, let us write down, this is almost equal to plus 1 minus x multiplied by 1 minus x Okay. So, it is very clearly this is a straight line equation that I have written already, and this is an equation of a parabola, because we have one x square term, correct, that is why. So, that is why whenever we plot this phi energy is there here, let us better do that, that becomes an inverted parabola. That is what you can see here. This is inverted parabola, and delta g, so this term here, delta g, what I have written this term, this is the term for the ideal solution, delta g is because of entropy change is shown like that, delta g m, that is the delta g of mixing. So, therefore, whatever you see in the books whatever you see that the delta g mix or delta g m, you will see delta g small, delta g either capital M superscript or small m superscript, that is basically because of the atomic mixing. And the top line, top straight line is basically the rule of mixture, that is the step 1. The moment you put two atoms side by side, they are mechanically mixed, and this mechanically mixing will lead to increase of a change of phi energy given by this straight line. So, if you add them together, you get the total phi energy of the system, that is what is shown on the y axis in this plot. See here, y axis and x axis is nothing but x. So, this is what is the real meaning of these kind of curves. So, that means if I have any solutions, any number of components, so that 2 or 3 or even more, I can actually, I will be able to calculate the phi energy mixing for the ideal solution. But actual solutions are not ideal, so we have to do something else, that we will do in the next few lectures, how we can calculate delta H, which we have missed here, which we have ignored here actually, or which we have taken as a 0. We will see how it is to be done. To calculate that, we need to use certain models, and these models are already dealt in the books, but we will see how we can use these different models and modify delta H equations. In fact, most of the thermodynamics of solutions or solutions actually are based on different models to calculate delta H. Delta H is calculated and given by this equation what I have derived, I have shown you just now. Only thing we are going to improve on is to calculate different parameters contributing to delta H. That is the way things are done in the books. So, let us move on. Now, so if I have a solutions, this is what I shown you of alpha. Alpha is a Greek alphabet. We use alpha, beta, gamma, delta in the phase diagram because they are easy to indicate solutions or liquid solutions, whatever it is. But we use always pure components for these non-solutions like pure AB or pure atoms. So, distinguish between these two is possible only by using Greek alphabets. So, here it is shown like this, it is a parabola inverted, and this line is missing here, there is no need to drawing it again. So, at any composition X, the phi energy change because of atomic mixing is given by this value, correct. The total phi energy is given by, we are drawing a dotted line this and marking as a G within curly bracket X. And as I mentioned, we always try to use a symbol mu for the pure components instead of GA0. In the literature you will find mu, but there is nothing wrong if you use GA0 also. GA0 is also used, but conventionally or rather across the world, the symbol which is primarily used to indicate the phi energy of a pure component is mu, and mu A0 is nothing but a phi energy per mole of component pure A, mu B0 is phi energy of component pure B per mole. Only when you add them together, phi energies will go change. So, therefore, our basic condition, that equilibrium condition is what? Equilibrium condition is, I have already told you, equilibrium condition is always given by dg equal to 0. That is your minimum phi energy conditions. The differential of g must be equal to 0. Now, if I differentiate g in terms of what? In terms of temperature, in terms of x, because there are two variables. And if you look at carefully, even if I do not assume pressure to be constant, there will be 3 variables. Pressure will be also built in here within GA0 or GB0. So therefore G is nothing but a function of 3 variables here. G is nothing but a function of temperature, pressure and x. Am I clear? That is what is the complete picture of the phi and of any solution. That phi and g is a function of temperature, is very clear, composition also is very clear, as well as it will be function of pressure. So that means if I take a total differential dg, that is nothing but df dt at a constant pressure and composition multiplied by dt plus df, this is del not d, sorry, del f del p at a constant temperature and composition dp plus del f by del x at a constant temperature and pressure multiplied by dx. This is mathematically correct equation. Total differential is nothing but partial differential multiplied by these differentials added together. Now we know that this is nothing but minus s, okay. It is better actually write g, okay, that is then it become easier to understand, otherwise it will be confusing better. So this del g by del t at constant pressure, we know that that is equal to minus s. Even if you do not know, I will just write how it is done, plus this one is nothing but volume multiplied by dp. What about this term? This term is what is known as chemical potential, that is what we have been discussing. This is known as mu, okay, mu of any components multiplied by dx. That is what we write. So that means total change of phi energy is equal to this. Now if I have many components, I write this is the way, summation I equal to 1 to n mu I dxi. Suppose you have 3 component solutions, then you will write mu 1 dx1, mu b plus mu 2 dx2, mu 3 dx3. That summation is what is taking care of atomic mixing. Atomic mixing part is coming from these summations. Well, as I told you, you may have problem in understanding these. How do I consider these parts? That is very easy to understand. Let me just explain to you. You will realize very soon how it is obtained. We know that G is fundamentally given by H minus Ts. So total differential is nothing but Th minus Tds minus S dt. Remember, this is total differential, this is not partial, okay. So I can modify this equation based on first and second law of thermodynamics. This is what? Del H is always equal to dE, because dE plus PV, H is E plus PV minus Tds minus S dt. Okay, so I can write down dE plus PdV plus VdP, that is equal to total differential of that. The moment d is put, that d is meaning that is total differential, so therefore it has to be differentiated through and through. Okay. Now we know that dE plus PdV as per first law of thermodynamics is equal to del Q, okay, and this del is different from this d because this del tells you that it is a path dependent function, but this is not a path dependent function, okay. So this is because work done is a path dependent function, that is why del Q. So VdP minus Tds minus SdP, that is what we get. So now we know that as per second law of thermodynamics, del Q is nothing but Tds. Why it is? Because second law of thermodynamics tells you the definition of entropy, and ds is nothing but del Q divided by T. So if you do that carefully, Tds get cancelled, so therefore you get Vdp minus Sdt. So, therefore, if I take a simple differential, del G by del P is equal to volume there you can see, and del G by del T is equal to minus of entropy. So, that is what we use. So, therefore, for a solid solution or a liquid solution, this is the fundamental equation of the free energy change. Now, I like to ask myself a question that if I have to know the stability condition for solid solutions, okay, then I must put in that equation this should be equal to 0. Okay. So, how do I solve this equation then? That is why we face problems, all of us face problems in solving the equations. We do not solve it, we are very clever persons. What we do? We simply put a tangent rule to the curve, okay, and tangent rule helps us things very easily. So, if I make a tangent across the at a particular point on this curve, that tells me the chemical potentials of these two components when this straight line meets the pure A and pure B vertical axes. So, that is why it is written mu A within curly bracket 1 minus x, mu B within curly bracket x. That means the chemical potential of B in the solution having x mole fractions of B, chemical potential of A in the solution having 1 minus x mole fractions of A. So, that is how do I arrive, I will explain in another class how do I use a tangent rule, that requires separate discussions, we will do that, okay, slowly one by one. And this straight line has equations is given by this is nothing but 1 minus x mu A plus x mu B, that is what is the equation of this tangent at a point x. Now, again it is shown in this curve we discussed. So, how do I consider stability? The stability is considered by using Gibbs rules, and they are given by mu A in phase alpha must be equal to mu A in a phase gamma, similarly mu B in alpha must be equal to mu B in gamma, where mu A are the chemical potentials of A, mu B's are chemical potentials of B, correct. So, graphically how do I do it? Graphically I simply draw a common tangent. Instead of a tangent, suppose this is the free energy of alpha, this is the free energy of gamma at a temperature T equal to T1, and so I draw a common tangent between them, and that common tangent will tell me the stability conditions. So, the stability conditions is obtained easily by extending these two lines, this tangent to both the particle axis. So, therefore, they will meet at mu A on the vertical axis x. So, this point is given by mu A alpha because this is a tangent to alpha, that is why. Similarly, tangent to gamma, therefore, this is also equal to mu A gamma, and they are sitting on the same point, therefore, their values are equal. Similarly, on the right axis is mu B alpha equal to mu B gamma. So, if any system, it does not matter, suppose it is a very complex system, you have many components and many phases, you simply write the condition like this. Okay. So, that must be satisfied. Similarly, if I have another component B, again same thing. It does not matter how many components are present. So, I can simply write this equation. So, this actually gives me in a multi-component systems where solutions are present or even phases are present, different phases are present from alpha to P. These are actually all conditions to be satisfied. The chemical potential at the interface between the phases must be equal of a particular component. Okay, so it does not matter whether this condition is very general, it does not matter whether it is a biomaterial, nanomaterial, structural material, micromaterial, whatever it is, but this is a fundamental condition. This must be satisfied, chemical potential must be satisfied. Now, I should stop here and discuss in more detail. I will describe what is the actual mathematical formula of mu. Okay. Basically, we know that mu has a particular functions, how it is dependent on we will discuss in details in the next lecture.